Hello, I'm Yang Itang. Today, our group member will be presentation for the risk analysis FL, LMS, and autonomous for the AI agent in the climate environment in the AI era. For our group member, it have me Yang Itang and Yang Qingxin, Zhao Yijia, Li Jiarui, and Hua Daoyang. For the background recent years claiming base of LMS and autonomous AI can have repeated integrate into business detection operations. However, this system inject normal security risks such like performance ingestion, memory patience, and again collocations. Well, it's hard to detection use traditional tools. For our project goals, it will be analyze architecture of climate-based LLM and AI against system. And second is identify common trait and risk propagation and patch. And third is study real world attack case and this technology machines. Fourth is their multi-layer defense framework use ENSA and NIST data. And the last is map out government requirement and share responsibility in security. The next page is charting overview. Overview of virtual GIS system is climate environment. For this system is structured into six instructor layer. Each layer has the unique the future, risk, and the definition requirement. At first is instructor layer will have API currency, WAP input valuator will be handle use requirement authentications and store validator. And the second is context layer. This technique is a context message response, current process approval, and current output. And third is plain models. It will be task declaration and action screens and tool solutions. Will be covering use goes into example planes. And fourth is sample layer. Fair cover Metro VMS app AL run test in scan sandbox. And the Ferros is currently sparse. It's a vector DB contained share in each message store share anymore and enable gate comparisons. At least its terminal server and object abilities for the database object store, claiming log, screen, and personal string and minimal. That's all for me. Next one.
In this slide, we present the conceptual architecture of a multi-engine AI cloud application. This framework outlines the interaction flow between various AI engine operation in the cloud-based environment. At the core of this system, we have a multiple layer each responsible for specific tasks such as user interaction, planning and execution. These layers communicate so the secure techno ensure the effective collaboration of agents. As we analyze the diagram, we see that each layer introduces potential security risk, which we will explore in the subsequent slide. Into the thread, moving on to the thread analysis. This slide shows a different layer of the system and their associated risk. For example, interaction layer is vulnerable to spoofing and denials of service attacks, which could lead to unauthorized access or service outages. The connection layer face risk related to information disclosure or tampering, which could result in public or corrupted outputs. Similarly, other layers like execution and external service introduce threats such as remote code, execution, data leaks, and log tampering, each with distinct impacts on the system integrity. The aim here is to assess those vulnerabilities systematically, ensure we have to adequate control in place to mitigate potential threats. This slide demonstrates the risk progression follow in multiple engine system. User chain over text starting from the integration layer. Text main initial with Marshall prompt bypassing input filter. This is followed by model tampering with the AM Mr. Bless program. Unauthorized action in the planning module. A misconfigured execution environment can result in a sendable issue. Finally, lateral spread occur as other engines ingress these pseudo vectors, propagating the attack. This illustrates how a single point of the failure can lead to cascading impact across the entry system. This slide shows a full diagram of the threat progression with the system. As demonstrated, the interconnectionness of the layer means that a breach of one point can compromise multiple system components. We need to design defense that only secure the individual layer, but also address how failures in one component can affect others. Diagram highlights the complex computation paths and shows security control can distribute across layers to prevent detect. By understanding these risks and their potential transmission paths, we can better secure the entry multi-engine system.
I'll introduce two common attack techniques against AI agents. First, prompt injection and jailbreak. Attackers hide special payloads inside user prompts, like using meta tags or invisible characters. Their goal is to trick the language model and bypass safety filters. Recent research shows about 30% of real apps are vulnerable, and over 15 jailbreak methods have been found. The main risks are unauthorized API calls, running tools without permission, data leakage. Second, memory poisoning and backdoor activation. In this method, attackers inject malicious data into the shared memory, or phantom models. For example, they add a hidden command like steal password. If the model reads this, it may follow the attacker's instructions without anyone noticing. Studies shows a 60% success rate even if less than 1% of data is poisoned. The dangers include hidden long-term control, privilege escalation, persistent data theft. These attacks show why we need strong security measures for AI systems. Now let's look at two more attack tricks. Third, multi-modal hijack. Attackers hide commands inside images or audio, so normal text filter can't catch them. For example, one image can secretly tell an AI to break the rules. in tests, just one picture infected a million agents. This attack spreads super fast and is hard to find. Fourth, cross-agent collusion. Here, different AIs uses shared memories to help each other attack. For example, one writes poison messages, another reads it, and cause damages. This can lead to major service outages, up to 80% in some cases. And because they work together, it's really hard to stop. Uh, these attack these attacks showed we need to protect all types of data, not just text.
Hello, let me introduce our group project, and my part is attack family and metric. Here, this table outlines our 4 major types of attack against AI agents, each with different characteristics in terms of success, risk, persistence, and scale. They have 4 types. The one is prompt injection. This is one of the most well-known attack vectors where malicious inputs are crafted to manipulate the model behavior, and the success range from 25% to 30%. And in turn to be alpha formula. Meaning the effect is temporal. It usually targets a single engine, and the memory processing. In this case, adversary aim to gradually process the model's internal memories or embedding over time. The success rate exceeds 60%, and it has a typically it affects multi-agent systems such as collaborative or federated environment. And the third type is multi-modal hijack, and this attack models that integrate multiple modalities like text and vision. According to GU, and it has a 100% success rate under certain conditions. It's unfamiliar in duration, but can scale up to cloud-level system, make it extremely dangerous in shared or automatic pipelines. And the fourth one is cross-agent collection. A relative low and emergence rate. This involves multiple agents collaboratively, intentionality or unintentionality, to produce harmful behavior. It has a success rate over 80% and is adaptive, meaning in evolve-based system response. It affects multi-tenant environment where multiple users share infrastructure. And this class, there is a classification about help us understand attack is success. The firmware overview to contact these threats. We propose a 5-layered defense in deep framework for AI agent operating in cloud. Each layer corresponds to specific area of the system architecture. The first one is the network perimeter control. This is the first line of defense using multi-TLS hard-ended API gateway and the web application firewall to restrict unauthorized access and enforce strict communication boundary. And the second one is model gateway import filtering. This one is help to probe serialization, scheme validation, and Unicode normalization. The third one is agent running time hardware. It can help to file check local virtual machine, AppOmo, or HMSA vector scene. And the fourth one is monitor logging incident response. It has the same as automated detection and real-time simulation. The final one is governance and compliance. The layer ensures long-term operation integrated through tools like REST framework, regular audit, or model calls. And this is my.
This page talks about how we manage and monitor the security of AI systems in the cloud. We use rules from frameworks like the Nest AI, RMF, the EU AI Act, and GDPR to keep AI system safe and fair. For example, we track how the model behaviors, such as how fast it replies or if it acts strangely. If something looks wrong, we send authors to teams quickly, like through PagerDuty or Slack. This helps stop attacks early and keeps our AI system trustworthy. Page 13 illustrates that data lifecycle management. In this part, we focus on how data is handled throughout its life. We make sure data is used properly, stored securely, and deleted when it's no longer needed. Data control helps prevent leaks or misuse. Managing the data lifecycle is a key part of the AI system safety, especially in shared cloud environments. And page 14 introduces that shared responsibility. Security in cloud-based AI is not just one-person jobs. Cloud service providers and customers must work together. For example, the provider protects the hardware and network, while the customer controls the data and model behavior. By dividing these roles clearly, we can avoid mistakes and make the system strong. Page 15. To sum up, our project look at the risks of using LLMs and AI agents in the cloud. We showed how attacks can spread across layers from prompts to memory and even across agent. Then we proposed a 5-layer defense model to stop these threats. Finally, we explained how both cloud providers and users need to cooperate to keep things safe. Page 16. In the future work, looking ahead, we can need stronger tools. For example, trust execution environment like Intel SGX can protect the model from spying. We can also use formal verification tools to make sure our rules work. Machine learning can help detect tricky attacks like poisoned data. And privacy methods like homomorphic encryption will help protect user data. In short, we must keep updating our defenses as AI threats grow.